This podcast is on assessing the presence or absence of multicollinearity in multiple regression analysis. Like the rough seas in the photo, untreated multicollinearity can capsize even highly worthy regression vessels, as we shall soon see. Multicollinearity, essentially defined, is the crippling presence of independent variables in a multiple regression model that are too highly correlated with each other for the regression output to make sense. We are unable to determine the true statistical significance of the independent variables in a multiple regression model when there is high multicollinearity present. Multicollinearity is a relative condition, meaning that it has to exceed a certain threshold in order to be considered to be problematic for the regression analyst. Multicollinearity is the regression assumption that is unique to multiple regression analysis. Thus, this is not an issue for simple or bivariate regression analysis, where there is only one independent variable. The high intercorrelation of the independent variables that we see in multicollinearity can come in several forms. A pair of independent variables may show high correlation, thus triggering multicollinearity. Also, a combination of more than two independent variables can be highly correlated with each other, which is also multicollinearity. To reiterate, multicollinearity can stymie the best of multiple regression models. It cannot be left alone. It must be corrected for in order for us to make valid inferences. If high multicollinearity is present, then there is no way to know whether or not the independent variables are statistically significant. In other words, multicollinearity bad. Why is it bad? It's because high multicollinearity produces large variances for the slope coefficients and thus large standard errors, biasing them towards statistical insignificance, when in fact they may be statistically significant. We will go over the mathematical reasoning for this outcome right now, so hold on to your hats. Let's define variance for the slope coefficient b sub I as equal to s squared sub b sub I, and s squared sub b sub I as equal to s squared sub u divided by v squared sub I, where v squared sub I is equal to the squared residual, or error in the regression model's prediction of the dependent variable, from the regression of each independent variable of all other independent variables in the model. Thus, v sub I equals the actual value of the independent variable being regressed minus its predicted value from the regression model. Now we'll take a breath, because that's quite complicated. But let's focus on the denominator, v squared sub I. If the result of x sub I minus x sub I hat is very small, then v squared sub I is small as well, and the variance b sub I will be very large. Thus, the more closely the independent variables are related to each other, the smaller the variation between the predicted value of the independent variable being regressed on all of the other independent variables and the actual value of the independent variable itself. Now, this is a big problem because the variation in the independent variables should be distinct from one another. And when it is not, then the analyst cannot be sure that any particular independent variable is influential in the model. Now, how do we know if there is too much multicollinearity to trust the true independence of the independent variables? We have four major indicators, and I list them from the surest sign of multicollinearity on the top to the weakest sign of multicollinearity, kind of in the middle of the slide, or on the bottom of the list. First, the model has a very high R-squared statistic, but it has few, if any, statistically significant independent variables. This is a real red flag that there is multicollinearity present. Second, the slope coefficients of the independent variables change greatly in value when independent variables are either added to the model or dropped from the model. That's also a pretty significant indicator that there is multicollinearity, because the coefficients, in fact, are very unstable. Third, the slope coefficients are unusually high or low depending on how the variables are measured. For instance, if your independent variable is measured from, say, 1 to 10, and your slope coefficient is 10 trillion, then that might raise some suspicion that there is a multicollinearity problem. Fourth, the slope coefficients have the wrong or theoretically unexpected sign. So what this means is that you hypothesize that the independent variable has a negative relationship to the dependent variable, and in fact, when you estimate the model, the slope coefficient is positive and significant. That's a pretty weak indicator, but a possible indicator of multicollinearity. The techniques to diagnose multicollinearity include each of the following: in order of least definitive, or merely suggestive of multicollinearity, to most definitive, where we in fact have a dead reckoning of multicollinearity being present in the model. The least definitive, but rather suggestive technique is to check a correlation matrix of all of the independent variables. A correlation of either plus 0.8 or higher, or minus 0.8 or lower, indicates multicollinearity might be present, but it doesn't prove that it's present. Much more conclusive is to regress each independent variable and all of the other independent variables and examine the R-squared values. If they're close to 1.0, then multicollinearity is indeed present. This is a more conclusive test, but it's a judgment call as to how close to 1.0 is the trigger for a declaration of multicollinearity. As a rule of thumb, an R-squared of around 0.80 or higher is a trigger. A final definitive technique is to inspect the variance inflation factors, or VIFs, for each independent variable. The VIF is generated from the formula 1 over 1 minus r squared sub I, which is where we have an r squared from a regression of each independent variable on all of the other independent variables. A VIF that's very high, and very high in this case would be greater than or equal to 5, is also an indicator of high multicollinearity. That also happens to be equivalent to an r squared of at least 0.80. Let's look at a graphic example of multicollinearity from an actual published research study. The scholar who performed the study was Gino Germani, and I'm circling Germani on the top right of this slide, who was a sociologist, a professor of sociology, at the University of Buenos Aires in Argentina in the 1950s, and Harvard University and the University of Naples in Italy in the 1970s. He was a famous sociologist. A research institute at the University of Buenos Aires bears his name. Germani, as a youngster, escaped Mussolini's fascist and populist Italy in the 1930s and had a lifelong interest in studying authoritarian political leaders who espoused populism, such as Juan Perón in Argentina. And I'm circling Juan Perón on the slide. Germani published an article titled El surgimiento del peronismo, el rol de los obreros de los migrantes internos, en desarrollo económico, Revista de Ciencias Sociales, in 1973. In this article, Germani wished to explain the variation in support for Perón in the 1946 Argentinian presidential election. This was a key election for Perón, as it was his first public plebiscite, and would establish his enduring popular appeal to the masses in Argentina. To explain Perón's support, Germani put forth the general hypothesis that Perón's support came from blue-collar workers who were in both rural and urban areas of Argentina. White-collar professional workers were hypothesized to not be supportive of Perón. Germani thus sought to capture as much information as he could in his model on urban and rural blue and white-collar workers. Germani also hypothesized that internal migrants who sought work in different regions of the country and are generally considered to be blue-collar workers would support a populist candidate such as Perón. Thus, as we can see here, the vote for Perón was estimated in several different models by Germani, and we're going to summarize the main results on this slide here. When we look at the results of this key regression equation, the results are rather surprising. So we'll quickly define what this equation is. Y is the percentage of vote for Perón in the 181 counties in Argentina, equivalent to US states. X sub 1 is the percentage of blue-collar workers in the county as a percentage of the economically active population in the country. X sub 2 is the percentage of rural blue-collar workers in the county. X sub 3 is the percentage of urban white-collar workers in the county. X sub 4 is the percentage of rural white-collar workers in the county. X sub 5 is the percentage of internal migrants. R squared is the R squared statistic for the model, and N is 181. That's the 181 counties in Argentina. Thus, it's a cross-sectional design taken at one point in time, the 1946 presidential election in Argentina. Now, what's surprising about these results? Well, if we take a look at them, workers do not seem to have a statistically significant impact on the vote for Perón. And what's really surprising is that the blue-collar workers, X sub 1 and X sub 2, don't seem to be anywhere near statistical significance. The absolute T statistics, that's always a positive numbers, will be in the parentheses, and they're associated with each one of these slope coefficients. So we can see for X sub 1 through X sub 4 that none of these independent variables are statistically significant. And in fact, they have odd signs. We would expect blue-collar workers to be supportive of Perón, but in this instance here, only the urban blue-collar workers have a positive sign. The rural blue-collar workers have a negative sign. Now, the white-collar workers do have negative signs, which we would expect theoretically, but they are also statistically insignificant. You'd expect them to be significant and negatively affecting the vote for Perón. The only variable that's statistically significant is this urban migrants vote, and that is positive and statistically significant. Again, slightly counter to the theory of Germani. So again, the conclusion is very unusual. Workers do not have a statistically significant impact on Perrón's vote. Now, Germani's work drew quite a bit of attention. And before we talk about the evidence of multicollinearity, we'll go back to this slide here. One of his readers was a political science professor, whom I'm circling on the bottom left, from the University of Iowa, named Peter Snow. Professor Snow was a well-respected authority on Argentinian politics, having written his doctoral dissertation on the rise to power of Juan Perón, as well as several peer-reviewed articles on the topic. Snow also taught himself multiple regression analysis. In fact, he wrote an innovative program in the Fortran computer language that generated regression output in the 1960s. In other words, Professor Snow was an ideal critic or a critical reader of Germani's work. Snow honed in on the stack of variables that Germani put forth that seemed to incorporate the entire possible universe of socioeconomic classes in Argentina. After all, what more is there to account for when you've accounted for the rural and urban, blue-collar and white-collar workers? In theory, it's a great idea to be so comprehensive in your modeling. But statistically speaking, throttling the possible variance into these four streams and these four streams alone does not allow for any baseline measurement of the impact of socioeconomic classes on the election. And this will become really important. Does this model display evidence of multicollinearity? I'm going to go ahead a couple of slides here. As we noted, the tests for multicollinearity are relatively straightforward. One of them is to take each independent variable and convert them to the dependent variable one at a time, and regress it on all of the other independent variables. We then examine the R-squared statistic for each of these equations. If they're excessively high, we know that there is a multicollinearity problem, because the independent variable is nearly a perfect linear combination of all the other independent variables. So let's look at these R-squared results of each independent variable regressed on all the other independent variables. Note that when x sub 2, and x sub 2, just to remind ourselves, is this urban blue-collar workers variable, is regressed on all the other independent variables, x sub 3, x sub 1, x sub 4, and x sub 5, the R-squared is almost a perfect 1. In other words, x sub 2 is an almost perfect linear combination of x sub 3, x sub 1, x sub 4, and x sub 5. That is a sure indicator that there is multicollinearity. Now, if that isn't conclusive enough, if we regress x sub 3, and x sub 3 is the urban white-collar workers variable, that is almost as high an R-squared value as x sub 2 is, where x sub 3 is regressed on x sub 2, x sub 1, x sub 4, and x sub 5, 0.98 of R-squared, almost a perfect multicollinearity situation. Same thing for x sub 1. X sub 1, when regressed on x sub 2, x sub 3, x sub 4, and x sub 5, gives us an R-squared value of 0.98. X sub 4 regressed on x sub 1, x sub 2, x sub 3, and x sub 5, not quite at that 0.8 level of R-squared that would indicate multicollinearity, but pretty close. And would be bothersome if we saw that, saw that R-squared present. But these three alone are very much indicators of multicollinearity. X sub 5 with a very low R-squared of 0.32 when regressed on x sub 1, x sub 2, x sub 3, and x sub 4, that's not a multicollinearity problem right there. But for sure, x sub 1, x sub 2, and x sub 3 clearly display multicollinearity. If we look at the VIFs, remember the key VIF is one that is greater than or equal to 5. Well, we see that for x sub 1, x sub 2, and x sub 3, VIFs of 50 and 100. Major problem. Well, what can be done? Because clearly Germani has a multicollinearity problem. Well, we can do several things. We could try to find more data. If we find more cases, we might find more variation on the independent and dependent variables. And the problem here is a variance problem. So with the greater variation, maybe we'll be able to solve our multicollinearity problem. We could try to combine independent variables into an index. If that is possible, then that would eliminate independent variables that are collinear to the dependent variable. We could drop offending independent variables. We certainly see that in Germani's equations, so we could potentially drop some independent variables. We could use the model for prediction only if the R-squared is high enough, and just say that we're not that interested in statistical significance, we're interested in explaining variation in the dependent variable. Or we could just give up, throw in the towel, and that's not the Bronco way of doing things. We're going to try to solve this problem. Well, to focus on Germani's multicollinearity problem, we can't gather more data. Germani gathered all the data for the 1946 Argentinian presidential election. The election is over. There's no new data to gather, so can't do that. We could try to combine the variables into rural-urban or blue-collar, white-collar workers, but then the meaning of the data would become less clear. We could try to say that we'll just try to predict values of the dependent variable, but the R-squared statistic for the model is pretty low, 0.24, so it wouldn't be a very good predictive model. In fact, the best solution is to drop an independent variable and re-estimate the model. So let's give that a shot. If we drop x sub 2, we find that the conclusions from this particular regression analysis are quite different. Let's look at these results. So if we look at, first of all, the t-statistics for each of the 4 independent variables remaining in the model, after dropping x sub 2, we find that they're all statistically significant. They all meet the rule of 2. So instead of a bunch of statistically insignificant variables, except for the internal migrants, we find that x sub 1, x sub 3, and x sub 4 are statistically significant and signed in the correct direction. X sub 1, urban blue-collar. X sub 3 and x sub 4 are the urban and rural white-collar voters. They are negatively associated with the Perón vote. The blue-collar workers are positively associated, and the internal migrants remain positively associated with the vote. So the conclusions turn out to be quite different. In fact, we find that there is populist support for Juan Perón, conclusive support, and it's quite the opposite of the finding in that particular article. So Germani should be happy that we have diagnosed multicollinearity and in fact rescued an important theory about the sources of populist support for presidential candidates around the world, but particularly in Argentina. So again, the R-squared is still relatively low, so it's not a predictive model, but it certainly does provide some key variation in Perón's vote explained. About a quarter of Perón's vote, in other words, is explained just by looking at social class. Now, what about multicollinearity? If we look at those R-squared values of each independent variable regressed on all of the other independent variables, when x sub 1 is regressed on x sub 3, x sub 4, and x sub 5, notice how low the R-squared is, 0.29. The other R-squareds, 0.38 when x sub 3 becomes the dependent variable, 0.20 when x sub 4 becomes the dependent variable, and 0.30 when x sub 5 becomes the dependent variable. Very far away from that 0.8 indicator of multicollinearity for the R-squared value. The VIFs are all very small as well. They're all under 5. So we don't see evidence here of multicollinearity. In other words, the problem's solved. Now, how do we know about this Germani multicollinearity example? Well, the final part of this case, Professor Michael Lewis Beck of the University of Iowa was a colleague of Peter Snow's at the time that Snow diagnosed this multicollinearity problem. Lewis Beck was writing a monograph on regression analysis and asked for permission from Professor Snow to use that example in his monograph. And this monograph has sold very well. In fact, we use a version of that monograph in our POLS 398 class. So this is, in other words, Lewis Beck, through publicizing Professor Snow's work on multicollinearity, makes us aware of an actual research issue or a research example where multicollinearity is present and how to solve for multicollinearity. Okay, well, that's a lot to take in, so we'll recenter ourselves for a moment. Just stare at this image of Mount Hood that I took from a plane several years ago. Thanks for watching. Hope you learned something about multicollinearity, and have a nice day.